Yeah, welcome back. Today we are going to learn about the discretized equation. I mean that Stephen's equation of the beam element. This content are included in the chapter 4 of the Logan textbook. 이번 주 6주차 강의를 하겠고요. 챕터 4에 있는 빔 시오리에 대해서 한번 저희가 이제 유한 요소 정식화를 한번 해보도록 하겠습니다. Let's begin to the lecture in English again. Today, learning object is driving the basic concepts of the beam. So, and then finally, we are going to drive the Stephen's matrix equation of the beam element, compared to the truss element. Truss element has only elongation or some compression in the only x-axis. However, the beam has some transverse displacement. I mean that normal displacement. So in the beam theory, we are normally we check the some deformation, actually deflection of the some solid structure. So in here, so we should check the displacement in the y direction. So maybe although beam include displacement in both direction x and y, however today we are mainly focused on the displacement in the y direction. So I mean 죄송합니다. So first we are going to solve the beam equation by the direct Stephen's method. So, and maybe we are going to also derive using some other potential energy minimum approach method or Galerkin residual method. However, you guys can easily derive the Stephen's equation using the direct Stephen's method. So, and then in this lecture note, we are going to learn about how to make some work of equivalent method. It is because that when you go back to your solid mechanical lecture, in the beam cases, we have several force. For example, in the beam element must consider the momentum or some other external forces. For example, we can apply the transverse load at the end of the beam. However, do you remember those kind of forces? This is a distributed force on the beam. Due to the distributed force, the beam maybe will deflect, looks like this, when we have those kind of boundary condition. So to apply those kind of distributed force, we should changing this force on the load force. I mean the nodal forces. It is because that when we assume that this is a single element, we can only apply the forces on only nodal point. In the middle of the element or inside the element, we cannot apply any forces. So that means that we should replace this distributed force to the specific point nodal forces. So that in here I'm going to introduce how to changing the distributed forces to the point nodal forces by the work equivalent method. So after running the replacing distributed loaded to the nodal forces, you can solve any problem related to the beam structure. So we are going to analyze several types of the beam structure which consider the distributed load or point nodal load both, so that we can also compare it to our FEM solution with the exact solution of the beam theory. So and then in the previous lecture we only I gave some homework, some bridge structure. So I think you guys can obtain some solution. This bridge is maybe consists of the truss element. However, when you replace the beam element, those results are slightly different when you consider some deflection of the beam structure. So that, yeah, I think the next homework is to the comparison between the truss and beam structure. And then after learning this beam theory for the FEM simulation, and our final goal is to the combining these two things in the same element. Actually, there are no simple truss structure in this world, just we assumed. And then beam theory, beam also consider the transverse displacement only. However, also all solid structure also experience the longitudinal direction displacement in the longitudinal direction. I mean that extraction or shrinkages. So that we should combining both two, so that maybe after the chapter 5, yeah, we are going to learn about the frame element. Yeah, this frame element means that combining the truss and the beam element. So the end of this chapter, we are going to also use some potential energy method or Galerkin residual method to derive the beam element equation. So that this is our running object in this chapter. Let's start the beam. So yeah, what is the beam? Yeah, beam is a long and slender structure member. Generally, yeah, they can consider the only transverse loading or transverse displacement due to some external force or external bending. So that compared to the truss element, so we are going in beam element, we are going to deal with the transverse loading or displacement or some momentum. So that to consider those kind of momentum and transverse displacement, so we should define this is a beam single element. Yeah, this is a first node. Yeah, this is a second node. So each node has a displacement in transverse direction and also some forces element in the transverse directions. So due to those kind of displacement, and also we should only consider those kind of deformation means that this beam structure move to the y direction, in the y direction. However, in the infinite small decimal element, so those kind of deformation can consider that there are some rotational movement, so that we only consider the rotational movement. Yeah, I cannot say that displacement in here. So, and then due to those kind of rotation, there are some resistance. We can call it the momentum. So finally, each node has a displacement and rotational movement, and in the displacement and rotational movement in the second nodes. So that means that this beam element has a 4 degree of freedom. And then also forces vector. In the forces vector, they have some force element in the first node and second node, and then in the second node we have some momentum resistance, and then here also momentum resistance. We can obtain the 4x1 pulse vectors. So although we don't derive yet of the local stiffness matrix of the beam element, however we can easily expect it. Local stiffness matrix size is equal to the 4x4 matrices. So due to some complex, I mean that beam has a more degree of freedom compared to the truss element, so that I think that a beam element more complex than a truss element. But anyway, it's very simple compared to the 2D and 3D cases. But please remember the in the beam element we are going to handle the displacement in the y direction and rotational angle. So, and forces in the y direction and moment and each nodal point. This is a basic. So that to define the momentum, we should know that the which positive value means that which direction, rotational direction. So that generally in the physics, we define the counterclockwise. Counterclockwise direction is always positive value. So that maybe when you grab some pencil in your right hand, this finger direction is a counterclockwise. So that this is my thumb direction is a positive direction. So you can please memorize how to define the rotational direction. So let's go to more detail about the beam theory, beam structure. To derive the beam stiffness matrix, we should know that the slightly different concepts of the beam theory. Maybe generally we have two types of the beam theory. First beam theory, I think that you learned in the last year in the solid mechanical lecture. So the first is Euler Bernoulli beam theory. And then the other things is Timoshenko's beam theory. This is the most famous beam theory. First one is more convention, or it follows the linear elastic relationship, but Timoshenko beam has some more different assumption compared to the Euler beam theory. To distinguish the difference between the Euler beam Bernoulli theory or Timoshenko beam theory, so we should know that what is the assumption of the Euler Bernoulli beam theory. So Euler beam theory is has some assumption. That assumption is the plane cross section is always perpendicular to the longitudinal central axis. Longitudinal central axis means that if we have those kind of some beam structure, which has some cross section area, but we only consider that in the plane 2D cases. So that this center line is longitudinal central axis. So that always cross section, this cross section, let's assume that this cross section in here, we can also have some cross arbitrary cross section surfaces. This cross section always perpendicular each other. So when you applied some forces, this due to the forces, the beam structure will deform. Looks like this, and then during the deformation, the central longitudinal axis does not change. This centroid axis always exists center or middle of the beam structure. So every point in the same when you make those kind of perpendicular line, yeah, this always indicate that they are cross section. So that means they're always perpendicular. So in here also due to the deformation, so maybe so this part will experience some increase the length. In means that they have a longitudinal elongation. Yeah, this line maybe will be shorter than the previous line, so that this line will be experience compression stress or some forces. So that however the plane cross section, yeah, I don't have a technique to draw the good quality images, but anyway, but so that always this cross sections, yeah, is always perpendicular longitudinal central axis. This is the assumption of the Euler-Bernoulli beam theory. Yeah, in the Timosenko beam theory, yeah, that at the cases, yeah, Timosenko does not perpendicular each other. Yeah, this is a difference of between the Euler-Bernoulli beam theory and Timosenko's beam theory. So in here, so you can easily say that, yeah, when you check the centroid axis, so yeah, so maybe, yeah, always, yeah, cross section has a perpendicular to the centroid axis. However, in here, if you feel the it's not the orthogonal, that means that, yeah, this beam structure does not follow the Euler-Bernoulli beam theory. So that this beam structure will be Timosenko beams. Yeah, this is a assumption of the beam theory. So that please remember the yeah, so that if you forget the details, so you can check the lecture material of the Professor Yang's classes. Maybe I heard that he used mechanics of the material textbook. So, and over there, yeah, I think that I actually, when I was a junior, I also learned solid mechanics using that textbook. Yeah, and there, yeah, there are many practical example and exercise problems, so that every time I solve it, so that I got a good score in the solid mechanics. But it's not it was not important. Yeah, so yeah, to solving some problem, it's not important. Yeah, important thing, you should know that what is the basic assumption of the solid structure. Yeah, I think you guys already know that what is the linear elasticity. Yeah, linear elastic is always proportional to stress, always proportional to the deformation, I mean the strain. So that, yeah, so those kind of relationship is very easy, yeah, to understand the concept. So when you solve some problem, yeah, you can obtain the solution by your hand or some numerical technique. So you can easily obtain the deformation or some stresses very easily. But the, yeah, real solid structure does not follow the linear elastic behavior. That means that we should consider the more complex theory or deformation theory. So yeah, all theories, yeah, actually our basic theory has a critical limitation. So that, yeah, if you want to mimic the real physics solid structure, yeah, deformation, so yeah, you can add some assumption. Yeah, this solid structure will be deformed differently. Yeah, for example, in the beam theory, yeah, Timosenko assumed that, yeah, this cross section, yeah, cross section does not perpendicular centroid axis anymore. So this is a starting point. Yeah, it is because that, yeah, solid structure is slightly different, shows a different behavior in the transverse displacement. So that, yeah, Timosenko want to explain some more accurately than Euler beam theory. So that, yeah, so that many researchers developed their own theory using the adding the basic assumption. So that so the important thing actually in this lecture we are going to solve some mathematical problem to understanding the concepts of the FEM. However, most important things is understanding theory. After the understanding theory, you can use very simply. Actually, all commercial software already implemented those kind of theory. However, without knowing the concepts of theory, finally we can obtain some solution. However, we cannot analyze or we can explain the result. I think that I already uploaded some homework and some example of the trust 2D trust system by console, and there I mentioned that please obtain some reaction pulses and external pulses by your hand after the obtain solution of the displacement and then multiplication with the global stiffness matrices. You can obtain the pulses vector, whole pulses vector. This pulses vector contains reaction pulses and external load pulses on the node. So we can obtain the whole pulses element after the multiplication global stiffness matrices and obtain the solution of the displacement. But the console, I think in my previous practice in console simulation, console returns on of the reaction pulses and the point load separately. When you follow my simulation lectures, so you can understanding. Without those kind of difference, actually, so you cannot know that or cannot understand why commercial software returned those kind of result. It is because that commercial software want to distinguish some already known value and unknown values. So similarly, we obtained some all displacement in the nodal point. However, some point we already know that due to some boundary condition. So remaining element in the node vector, displacement vector. So we finally obtain the solution after the applying boundary condition and then some linear algebra, solving the linear algebra equation. So and then we can obtain the whole displacement vectors. And similarly, pulse vectors is directly obtained by your some matrix multiplications between the global stiffness matrix and pulses vector. However, console think about that. I'm going to as console software is going to return the unknown pulses vector, pulses element, and already known pulses element separately. So that when you're understanding those kind of concepts, you can very freely use the commercial software. So that but this is not important. However, I want to explain more those kind of things for you guys. So anyway, so Timosenko beam theory, Euler beam theory has always perpendicular centroid axis. However, Timosenko does not agree those kind of assumption. It is because that cross section maybe has some different angles. So that Timosenko won't show those kind of difference solid behavior. But Timosenko beam also follow the linear elastic behavior. So there are some only slightly big difference. So that in here, so only difference is the line. This in here, line is different. That means that some strain in this maybe strain in the axis strain direction, and position in they use a g direction. So at the g, maybe in the g, z is equal to h, is different, maybe not different in the axis. This is a Euler beam theory, and then this is a Timosenko beam theory. So they will show a slightly difference. So that, but maybe I'm not sure that Professor Yang taught you guys about the Timosenko beam theory. However, Euler beam theory is enough to understanding the concepts of the FEM method in the beam element. So only difference is that they added some angle distribution behavior, so that they added one more those kind of very simple theory. So that when I was born, if I were born 100 born earlier, maybe 100, that I think that I thought that I can develop those kind of theory early than Timosenko. Sometime I imagine, but first only imagine first is very important. So that please be ambitious or have a high goal, dreams. Making something different is very simple. Just adding one more thing than other guys' work. So this is a big find or some development. I think that so that I think you guys can become a good engineer or scientist. So if you demonstrate more one thing more dimly, so and then you can find one more one step progress than other guys. So I think that you can become a good engineer or scientist. So anyway, so to check the beam theory, Euler beam, Bernoulli beam theory, we should I select some small infinitesimal small element. So in here, that the length is dx. So that left hand side, so that they will have a transverse load in this positive direction, and the momentum is also positive direction in this side. So that depending on the your solid background knowledge about solid mechanics, this is both is positive direction. It is because that this is opposite side. So that, but anyway, so that to match the some equilibrium, so the momentum will be added from m to delta m. So that due to the changings of the position, and then also transverse load will be added more dV. So when you see those kind of thing, what do you think we should check first? In the solid mechanics, always match the what? Pulse equilibrium. In here, y direction always equal to 0, and then always momentum is always equal to the in equilibrium. So that when you see those kind of solid structure, so you should check the pulse equilibrium and momentum equilibrium. This is the basics of the our solid mechanics. I think that this is a whole things about solid mechanics. So when you check the pulse equilibrium in y direction, we have pulses in y direction, positive direction, and v plus dv, it has a minus sign. And then I forgot the pulse distributed pulses. This is a distributed pulses. So that to match the unit of the pulse, so we should add the this is a unit Newton per meter. So that we should add it multiply the length more. So that, and also this direction is a negative direction, so that please add it minus sign in here. And also yeah, we can obtain those kind of thing. Yeah, this is v, it can be cancelled out. Yeah, minus dv minus w dx equal to this one. So that maybe finally, yeah, we obtain the w, yeah, equal to the dx dv. Maybe we need minus sign. Yeah, so we obtained those kind of some relationship. So, and then from the momentum equilibrium relationship, yeah, here, so yeah, momentum, yeah, we should check the momentum equilibrium every point. However, yeah, if you the, yeah, and I want to check the at point 2 here. So yeah, we have a momentum m here. So where is the momentum? So maybe, yeah, yeah, this has some negative value, right? Yeah, it is because this is a clockwise direction, so that minus sign. And then in the point of point nodal point 2, yeah, this is also generated momentum behavior with the momentum arm dx. So that, yeah, and then this movement also clockwise direction, so that minus v dx. And here, so, and then, yeah, this transverse load does not generate the momentum. It is because the momentum arms equal to 0. However, in here, yeah, we have some momentum. Yeah, so we should check. Yeah, this is a counterclockwise. Must be it has a positive sign. And also, yeah, this distributed forces can generate the momentum movement maybe in this direction. So that how can you obtain the, so that, yeah, those kind of distributed force can be replaced some equivalent forces. Yeah, total forces is equal to the w dx. So that maybe this here, yeah, center point, middle point, yeah, can be equivalent point. It is because that all points generated these forces and this momentum arm and these forces and this momentum arm, these forces and momentum arm. Yeah, so, yeah, so total summation of the momentum equal to the generated by point loaded forces and then this momentum arm. So that we can say that this, yeah, w dx and equal multiplication the half of the length of the element dx over 2, and then in this direction is a counterclockwise direction, so that this will have a positive direction. So that w dx and more dx equal to 0. Yeah, this m cancel out each other, and where is more things. And then, yeah, so I want to obtain those kind of relations more simply. However, it's more slightly, yeah, how can we obtain those kind of relationships? Yeah, this solid structure is very infinitesimal structure. I mean that very small size. So that, yeah, dx square is too extremely small compared to the other values, so that we can negligible these two things. Yeah, if you this solid structure deformed very small size, yeah, this is assumption. Or sometimes, yeah, we can neglect I do not apply those kind of yeah, distributed forces, but yeah, this is a wrong assumption. Yeah, it is because that in the previous here, yeah, we say that distributed forces is equal to the changings of the transverse load at the specific point. So that, yeah, this is not the correct assumption, but yeah, this square yeah, is too small. So that finally we can only consider these two terms, yeah, v dx equal to dm. So that finally we obtain those kind of relationship. Yeah, this is the basics of the beam theory. So that, yeah, transverse forces, loads equal to the momentum changing. So that I think that this is I think that you can derive in the solid mechanics structures. So yeah, with those kind of assumption, in the next slide we need those kind of relationship. I'm going to dx equal dm, and here in the previous slide, distributed forces is equal to the dx and dv with a minus sign. So we are going to more obtain the other some relationship. Here our solution is some strain in the x direction is equal to the some v is a displacement in the y direction. Displacement. So that this is a second derivative of the y displacement equal to the multiplications of position y. In here, what is the position y? So that we have when you selected the centroid axis, so that this is a position y. In here y equal to 0, but in this side, so that this is some shift from the centroid axis, so that strain is equal to the shift from the centroid axis, and then some here so curvature. So that I think that you guys learned about the why this strain has those kind of relationships. So in here, what is the curvature? Curvature is inverse radius. So if you the flat beam, the curvature is infinite actually, but due to some forces, the beam will be deformed, looks like this, and then due to the deformation, upper part, the length must be higher than centroid axis. Below part length is must be lower than centroid axis. That means that upper part experience elongation, below part experience compression. That means that there are some elongation strain. Below part they have some compressive strain. These two, this is also same solid structure. Young's modulus must be equal to all position, so that we can say that the stress is varies from to the bottom surfaces and top surfaces. So so anyway, due to the difference, variation in the stress, so that momentum will be generated in the some specific cross-section area. So this is our basics of the beam theory. However, in here we are going to derive more things. First, please remember that so they mentioned that this beam solid structure will have some curvature. That means that there are some circle shapes due to the deformation. This is when you assume that this is r is a radius of the some curved shaped solid structure. So that although I mentioned that this is zeta, for some time you can say that slightly changes of the zeta angles. So and then anyway, due to the some we can check the some solid part structure in here. So that I want to check the actually unit length in here, or sometimes is equal to the dx small size. So that from the relationship, this length equal 1, always equal to 1 in here. It is because that centroid axis length does not changing due to the deformation. This is assumption of the Euler-Bernoulli beam theory. So that the length is always equal to 1. Right? So that from the relationship arc length and radius, how can you define that L equal to R zeta maybe? So that they means that 1 equal to the R is capital R and the zeta is always zeta. So that from here, this relation obtained those kind of thing. And also in this part, I obtained the exhumed images in here. So that in here, so I defined the this is a length is a y, and here so that equal to y, and then the this part will be increased actually, so that this I indicated as epsilon. This from the triangle relationship, similarly, or some arc length relationship, same. So the total strain is equal to the theta r is y, so that we obtain the same relationship in here. So this is the first thing. So that from these two relationships we obtain the some increment of the length is equal to the r over y, or some curvature equal to y. This is a relationship. Depending on your position, sometimes we can say that this minus sign, why we need the minus sign in here? It is because the upper part increased more. However, below part, when you use when in the similar manner, so that we can obtain the minus shrinkages, so that at that cases you need the minus sign. So anyway, so but until here we can obtain the relationship in here, but we don't know that y curvature can be expressed looks like this. So next part is for the explanation of the curvature and displacement in the y direction relationship. So that then here, in here, you can easily think about this is r, or the same. I copy and this figure from another textbook, so they use a different note indexes. So in here, so also you can say that this theta may be using the same notation in here. So and here, v is a displacement in the y direction. So when you think about this is some deformation of the solid, some structure. So we obtain the v displacement, so that this v indicated that displacement in the transverse through the axis. So it makes some confusing, so I'm going to neglect. And here, so first, I want to derive this relationship first. So how can we obtain the v? First in here, so let's assume that first time, the curvature is infinite, maybe, so that this value is infinity. So that, and anyway, so that due to the deformation, this solid structure will changing looks like this. This can be indicated looks like this, and then due to the angle change, due to the deformation, angle is changed. So how can we obtain those kind of things? First in here, so so anyway, due to the deformation, that means that, so anyway, there are some changes in the y displacement and with respect to the movement in the x direction. So that means that we can easily say that, so in here, dx, and then from here the movement in here dv, so that this is equal to the theta. From the tangential relationship, dx of the dv is equal to theta. You can easily obtain this relationship first. I think that very simple relationship. And then we need one more things. Here, so movement in the theta maybe first, maybe from the previous relationship, maybe theta, but for your convenient, easy to convenient, I'm going to changing those kind of relationship. And then actually theta, first time theta may be equal to 0. However, due to the deformation, theta will be changing to d theta. So that means that also dx d theta is also equal to the y. We can see those kind of relation in the previous slide. Although I mentioned that this equal to the 1, but I say that if we can check the dx, and then curvature is equal to always r, radius is always equal to r, and zeta, if you want to select the length is dx, and it becomes d zeta. So that from the relationship also we obtain those kind of relationship, so that you can add it here. So one more time, so that finally we obtain this is a curvature, so that this is a second derivative of the dx d zeta, and then this is a finally we obtained those kind of relationship looks like this. Every time I forgot the derivative, how to derive this relationship, but please remember until the final exam. So we need I think that it will be very helpful to memorize the relationship. You can easily solve some beam theory problem easily. So anyway, this is finally we obtained this relationship here until here, and then in these stages we are going to derive the momentum in here. So I mentioned that this upper part will be experienced due to some elongation, so that has some tensile stress due to the elongation, so that maybe however in the central point there are no stress at the central point axis. However, there are some due to the shift that we have going to have some strain and here in the position y, but strain direction is x, is always equal to the here previous in here, so that position y and curvature, so that we do not know the exact curvature yet, but if we central point axis means that y equal to 0, so that there are no strain in the central point of the axis, but due to the offset to the y, so that we obtain those kind of strain. That means that from stress is a follow the Hooke's relationship. So but I mentioned that although we added the minus sign, but in this sign we don't changing the sign due to the elongation, but the below part due to the minus offset, this in here stress is different sign but same magnitude, but this part positive sign stress or pulses, and this is a negative sign direction. I mean that in here we obtain those kind of thing. They can generate those kind of momentum movement, so that due to the stress variation, so in here stress 0, however maximum stress is on the top surfaces maybe, so that this is a value, and then so due to the stress variation momentum is generated. How can you obtain the total moment? Actually total moment is a summation from to the minus y plus y, that the stress and then cross-section area and then difference, momentum arm difference, but we don't, we can say that dA. So and then momentum arm is y, so that this is a stress sigma, and dA is pulse, and then y is momentum arm. This is equal to has a same unit of the momentum arm, so that you can changing using this one, but due to the match the correct direction, you should add some minus sign in here. So that in the previous slide, so that this stress is equal to the strain and y, and curvature is equal to the second derivative displacement in the transverse directions. So that, and we have a 2y, and then finally reached and then stress sometimes has a minus sign, actually exactly correct, so that this become the positive sign, and then Young's modulus and y square, and then second derivative in y displacement looks like this, and then in Young's modulus does not independent with cross-section area, and then transverse displacement also independent in here, so that this, what is this? This some y second square integration or cross-section area, that means that inertial momentum, so that we can say that this is equal to the I, so that finally we reached those kind of relation. Momentum is proportional to the Young's modulus and cross-section area, and then here. So this is the basics of the Euler beam theory. So please do not forget the nth final these relationships. So in the previous slide we reached those kind of relationship. Momentum is over the Young's modulus, and inertial momentum is equal to the curvature, and curvature is equal to the second derivative in the of the transverse axis with respect to the x. So that, and then in the first part, we obtained those kind of relationship. Transverse forces is equal to the changing of the momentum, and the distribution forces also changing the transverse route. So that in here we obtained what is the momentum, so that we obtained those kind of relationship and distributed forces, and looks like this. So finally we reached some those kind of relationship. And then finally, when we assume that Young's and inertial momentum is constant and force act on the only nodal point, it is because that in the FEM simulation, we only consider the nodal displacement and nodal forces only. Inside in here, we don't have any information, so that means that distributed forces is always equal to 0. So that means that finally we obtain some relationship in here. So maybe in the classical solid mechanics, I think that maybe you guys obtained some solution, maybe first nodal polynomial equations after the boundary, applying some boundary condition. I think that to obtain the solution, it's easy. So just integrated part1, and then we obtain the part unknown integration constant, so that we need at least part boundary condition to some solution, so that this is a assumption of the to obtain the solution of the transverse displacement, we should know that at least part coefficient. So this is the same way, but in until-truss element, we assume that displacement field is a linear or first order polynomial equation. However, to mimic the beam deformation, so we need a third order polynomial assumption. So this is a starting point of the deriving the stiffness matrix of the beam element. So that in here, so we got those kind of relationship, and then we are going to assume that displacement field follow the third order polynomial equation. So it is because that why we choose the u displacement is first order polynomial equation, but in here we have only considered the displacement in the each node point. We have two displacement value. However, in here, so we have two displacement and two angle rotation more, so that we have a 4 degree of freedoms. So that means that we should check the part1 coefficient more than for coefficient unknown variable. So that's why we use those kind of solved or the polynomial displacement function. So this is a starting point. Yeah, let's obtain the coefficient detail. Yeah, at here x equal to 0. Yeah, exact value is always equal to the v1. Yeah, actually you don't need to the indexes y in here. Yeah, v already indicated the displacement in the y direction. Yeah, so that, and then we assume that we follow those kind of relationship. So 1, 2, 3, 4. That when added the 0 value in here, so that always a4 is equal to the v1, and then x equal to L here, so that at that point, yeah, displacement is equal to the v2. Yeah, we don't need to the y subscription, and then x is equal to L, so that yeah, we obtain those kind of relationship. And then we should check the angle movement phi. Yeah, in the previous slide we say that the theta is equal to the dv dx, so that yeah, x equal to 0 at that point. Yeah, theta 1 is equal to the, yeah, how can you obtain those kind of things? Yeah, when you derive the 3a1 x2 square and 2a2x and then a3, and then when you added 0, 0, and then remaining a3 is theta 1, and then similarly theta 2 is equal to the 3a1 l square to a2l plus a3. So it looks like this. So that yeah, we want to know that coefficient a1, 2, 3, 4 exactly, and in here you apply the 4 boundary condition. That means that you can obtain the some exact values in about the coefficient a1, 2, 3, 4, and the total vx is I'm going to skip detail, so that this is a1 and this is a2. Yeah, this a3, this is a4. Yeah, very simple. Yeah, so yeah, you obtain those kind of thing, but let's back into the truss element in here. So that in here, so although we obtained some relationship when you apply some boundary condition, so but anyway finally we say that the final relationship and looks like this, and then so 1 over Lx, yeah, so those kind of things. But finally we mentioned the shape function. Yeah, same manner. Yeah, so we can organize v1 and v2, yeah, theta 1 and theta 2, so that those kind of way, yeah, we are collect, yeah, force vectors look like this, and then finally, yeah, you can reach those kind of relationship. And in here, first check the v1. V1 has a 2 over L3 and x3. Yeah, 2 over x3 L3. Yeah, this is the second part. And then in here we have yeah, this is a L square minus 3. Yeah, minus 3 with the x square. And then yeah, where is the phi v1? Yeah, there are v1, so that we can 1, but due to the this coefficient, yeah, this becomes the L square. Yeah, so that you can obtain those kind of thing. Yeah, this is what is thing. Yeah, this is shape functions of the game element. Yeah, before we go further, so we should check some relationship. Yeah, this Helmut cubic spin-line function. So yeah, that has some relationship. Yeah, each shape function can become, yeah, when a1 is equal to 1. Yeah, at the time, yeah, a2, a3, a4 become 0. Yeah, similarly, a2 when a2 equal to 1, yeah, a1, a3, a4 become 0. yeah, this is a characteristics of the shape function. And then yeah, second next characteristics is maybe a1 to equal to not 0, sorry, yeah, become 1. This is a second characteristics of the shape function. So that those kind of function is actually interpolation function. So yeah, can you go back to the 2 years ago? I think that you guys, most guys, met in the numerical method lecture. So that, and here I taught you guys about the interpolation or some regression method. So that among those kind of method, so that this is a very simple, yeah, interpolation method actually. Yeah, so yeah, FEM method is also techniques of the interpolation method. So yeah, numerical method is a basics of the some. You can know that specific value at specific point. However, yeah, we hope that to obtain the whole field variable. That means that we want to know. We also want to know that the between inside element some of the variable, so that we are going to use some interpolation technique actually. So that FEM method is also same method of the some interpolation technique. So anyway, so in the previous slide, yeah, you guys can reach those kind of some relationship. So, and then next thing is what is the next thing? Define the stress and displacement and stress and strain relationship. Yeah, and then we already discussed about the Euler beam theory. Yeah, strain follow those kind of relationship, but yeah, so sorry, right, yeah, so displacement in the x direction follow looks like this, but please remember that stress relationship, those kind of relationship, maybe, yeah, minus curvature, yeah, k is curvature, yeah, those kind of relationship we already derived the detail. So that finally, yeah, next thing, how can you derive the simply matrix equation? Yeah, so yeah, we already applied some boundary condition. Yeah, what is the boundary condition? V1, yeah, V2 is a displacement value, and pi1 and pi2 is a rotational angle boundary condition. So that, yeah, anyway, we know that those kind of field variable of the displacement, so that with the multiplication of the local stiffness matrices, we reach the some forces vector. We can obtain the some forces vector in here. Yeah, we want to know that momentum and shear forces. Yeah, so that or we already derived the some relationship. Momentum is has this kind of relationship, and shear forces also has some relationship, those kind of relationship. But in here, m is follow this relationship, and then finally shear forces has some third order difference equation relationship. Yeah, so anyway, yeah, so in here, this V shear forces has some field variable, but in here, yeah, when x equal to 0, yeah, momentum is equal to the m1, yeah, momentum at first nodal point. And then what is the second boundary condition? X equal to L, yeah, that follow the second m2. Yeah, in the shear displacement, yeah, y, x equal to 0, yeah, right, first in y, and then displacement at or, yeah, this equal to this one. Yeah, here I prepared those kind of thing. Yeah, f1y is one value, the x point, x equal to 0 values in here. So that, yeah, we in the previous slide we had some those kind of relationships, so that you should take derivative 3 times, so that, and then when you finally add it equal to 0, so finally we obtained those kind of relationships. And then when you added the boundary condition, you can check those kind of things. So that please try it one more time. I don't have enough space to write down more here. So and then similarly, we obtained those kind of relationship, and then second momentum, and then looks like this. So and then we reached those kind of forces vector in here, and this is a displacement vector. So that in here we same coefficient ei over the L3, and then here 6L at 2L square minus 6L 4L square. So that right, this is a local stiffness matrices of beam element. This is how to drive the local stiffness matrices. Compared to the truss element, it takes more time to drive the local stiffness matrix of the beam element. But anyway, finally we reached those kind of 4x4 local stiffness matrices. And here, so this local stiffness matrix also has some first characteristics. What is the first characteristic? First characteristics is symmetric characteristics. And then what is the second characteristic of the local stiffness matrices? What? Can you remember that? Singular matrix. What is the singular matrices? They don't have inversion matrices. So that without the boundary condition, more specific boundary condition, we cannot obtain the solution. So and then this beam structure only consider the transverse forces or displacement and bending momentum. In here we neglect the axial forces effect in here. So that I think that you guys are very smart. So our final goal is obtain those kind of relationship. The first one, U1 and V1 and pi1, U2, V2, pi2. And here, K is a local stiffness matrix. But I think that you guys can easily obtain this local stiffness matrix. It is because that you guys already know that the axial effect follow the truss element. Transverse movement or bending movement follow the beam equation. That means that you can easily combining these two solid structure in the one FEM equation. So that in the chapter 5 we are going to more discuss about the detail, but it's so mathematically hard to solve it, but concept is very simple. So that I'm going to skip the chapter 5, more discuss about the other things, or chapter 6 or some substructure in the chapter 5. But depending on our course schedule, I'm going to changing more. So anyway, so I think that we have spent enough time. So so I'm going to so let's go to the further. So next thing is about the summary of the Euler beam theory. So that, but it's not the big issues on in here. So this beam element is Euler beam theory. We assume that very simple. Beam is very long and slender. Euler beam theory has some assumption. Euler beam assumption of the beam has a very long length or very thin structure. It is because that those kind of solid structure, and then this solid structure will deformed and looks like this. Euler beam theory has some assumption. Cross section always perpendicular to the axial centroid axis. But let's assume that those kind of very short and very thin solid structure, that due to some forces, this solid structure will deform, looks like this. But at this time, all cross-section area perpendicular each other. So due to the some I think that you guys know that already, Poisson effect. So that due to the some deformation, so that there are so many material in here, so that they will experience some large compressive stress due to the some Poisson effect, so that the behavior movement is slightly affected by the existence of the materials. So that we can say that those kind of Poisson effect in here, so that those kind of perpendicular assumption does not match anymore in the very short and thick beam structure. So at that time you should changing the theory. This is a Timosenko beam theory. So in this case, what is the wrong? So what is the short? We cannot say that exactly which length is long or short. However, when you simulated, when you analyze some solid structure, at that time please remind that this solid structure is some high aspect ratio. I mean, the aspect ratio is length and then cross-section lengths. So that if they have a small ratio, at that time we cannot use. At that time, this Euler beam result give us some big error compared to the real physics phenomena. So at that time you can changing the other theory to mimic the real physics solid structure. So this is a basic assumption of the. And then Timosenko beam has there are some more additional theory, but this is not our scope, but it's more complex than So when I introduce something, so that I think that you guys already know that some rotational difference. However, in the Timosenko beam theory, there are some two big issues. That first, due to the some longitudinal transverse load. In the previous Euler beam theory, all theta rotation is generated by the some I forgot the details. So due to the momentum, however, and then there, so that they added more term, so that Timosenko beam added one more rotational movement, so that due to so they added one more angle distribution. Some rotational angle is a summation of the two effects. First is a transverse forces, and then the other is a momentum behavior. So they added these two terms, so that at that time does not the perpendicular anymore. So that this is how to obtain the Timosenko beam theory. So anyway, so when you consider the Timosenko beam theory, so that compared to in the Euler beam theory, we obtained some one more theta beta angle movement. So that total behavior changing and looks like this. So when you added one more term, so that you can finally obtain those kind of relationship, but please do not use those kind of thing. In our textbook, they do not derive the exactly, so that we cannot use this equation. So maybe you are interested in the more detail, please join the graduate school. Yeah, in the graduate course, I'm teach about more detail about FEM method. So, or when you learn about elasticity, yeah, in the graduate course level, so that you can understand what I want to say. So, yeah, I stopped today the lecture so that until this lecture, so we can obtain some relationship of the displacement and momentum, transverse momentum and rotation and some momentum. So we finally obtained some local stiffness matrix equation for the beam element. So that using the beam stiffness matrices, we are going to assemble the designing, analyze some solid structure. So that this is a basics example. This is today's lecture. So that maybe next week we are going to discuss about some practical example, and then I'm going to introduce some converting method of distributed forces load and to the point loadal forces, and then finally using Galerkin residual method we are also we can derive this local stiffness equation for the beam element. 예, 오늘 잠깐 먼저 빔 요소를 증명하는 것까지 한번 해봤고요. 트러스에 비해서 빔이 조금은 좀 지저분하죠. 왜 그러냐면은 빔이라는 거에는 저희가 이제 수직 방향으로의 변이랑 그 다음에 회전하는 앵글에 대해서 두 가지를 동시에 고려를 해야 됩니다. 그러다 보니까 자유도가 두 개로 늘어났고요. 그러다 보니까 우리가 변위장이라고 하는 거를 바로 어떻게 정의를 해야 되죠? 예, first order, 그러니까 1차 폴리노미얼 이퀘이션으로 정의를 하지 못하고 3차로 가정을 해서 풀어야 됩니다. 예, 그래야지 저희가 이제 원하는 솔루션을 그래야 그 정도 3차 정도는 해줘야지 최소한 아주 간단한 빔의 Y 방향의 변이랑 회전 각도의 변이를 저희가 도출을 해낼 수가 있고요. 예, 그거보다 적은 걸 쓰게 되면은 모든 값이 0을 만족하기 때문에 애초에 사용을 할 수가 없습니다. 즉 그러다 보니까 그 안에 사용된 요소가 쉐입 펑션이라고 했던 데가 앞에 트러스나 스프링 엘리멘트랑 달리 1차가 더 이상 아니죠. 그러다 보니까 2차, 3차가 조금 들어가 있습니다. 그래서 비선형, 사실 선형 요소라고는 할 수 없고 이제 비선형 요소라고도 하는데요. 그래서 이런 애들을 좀 사용을 하는구나 라는 것까지도 조금 기억을 해주시면 좋을 것 같고요. 예, 저희가 이제 이렇게 빔으로 갖다가 했던 거를 갖다 사실 트러스랑 접목을 해가지고 이제 할 거고, 사실 트러스로만 가지고 제가 숙제를 내드렸는데 그 숙제 값이 정확하지는 않습니다. 그래도 이제 빔까지 하시게 되면 조금 더 리즈너블하게 변형을 갖다가 묘사를 할 수도 있으니까 원래는 빔을 더 많이 쓰긴 하는데요. 여러분들에게 매트랩으로 빔 코드까지 짜라고 하면은 너무 이제 복잡해지다 보니까 이제 어떻게 보면은 이제 매트랩이랑 콘솔이랑 손으로 비교하는 거는 아마 트러스까지 주로 할 예정이니까요. 그렇게 조금 기억을 해주셨으면 좋겠고요. 빔부터는 이제 사실 빔이랑 트러스를 합쳐서 이제 콘솔에서는 아마 보여줄 것 같은데요. 그런 경우 이제는 저희가 이 로간잭슨 프레임 엘리멘트라고 표현을 하고 있습니다. 그러니까 빔은 회전과 수평 방향의 변이만 얘기를 하는 거고요. 거기에 이제 다시 트러스처럼 이제 엑시알 방향의 변이까지를 말을 하고 싶으면 이제 빔과 트러스를 합친 이제 프레임 엘리먼트라고 챕터 5에서 얘기를 하는데, 그 두 개를 합치는 건 사실 뭐 그렇게 어려운 방식이 아니기 때문에 그 부분에 대해서 이제 자세하게 설명을 하진 않고 그냥 챕터 5는 아마 스킵을 거의 할 것 같습니다. 뭐 그렇더라도 뭐 좀 저희가 이제 어떻게 보면 1차원에서 사용하는 요소거든요. 트러스 빔이라는 게 빔이 물론 1차원으로 표현이 안 되고 3차식으로 표현이 되고 있지만은 X라는 1차 함수만 쓰고 있기 때문에 1차원 요소들이라고 말을 하고 있습니다. 이 정도까지 공부를 하시게 되면은 1차원으로 표현할 수 있는 모든 시스템에 대해서 거의 이제 됐다라고 볼 수도 있긴 한데요. 물론 사실 이제 이런 걸로 가지고 저희가 복잡한 빌딩 스트럭처나 이제 브릿지 스트럭처를 갖다가 설계를 하고 디자인을 할 때는 쉽습니다. 근데 실제로 건축이나 이렇게 부품을 설계하시는 분들 이런 요소를 쓸까요? 예, 거의 쓰지 않습니다. 사실은 왜냐하면 이제 실제로 2D나 3D를 시뮬레이션 할 수도 있고요. 그게 아니고 정말 너무 많은 복잡한 구조를 할 때는 1D 요소를 많이 쓰고 있습니다. 특히 건축 같은 데서 남자분들 EPL 구단 같은 거 축구장 같은 데 보시면은 프레임으로 막 엄청나게 크게 돼 있잖아요. 올림픽 경기장이라든지 그런 것들 보시면은 엄청 많은 요소들이 들어가 있습니다. 컴퓨터로 풀기에 부담이 되기 때문에 얘네들을 최대한 리얼리스틱하게 꾸며야 되기 때문에 1차원 요소를 많이 쓰고 있습니다. 저희가 배웠던 트러스, 빔 엘레멘트를 가지고 이제 그런 스타디움의 안정성을 갖다 해석을 하는데 선형으로 풀기에는 복잡하잖아요. 너무 단순하잖아요. 그리고 실제로 재료가 선형 거동을 안 보여줄 수도 있는데 그러면 뭐죠? 이 1차원 요소를 조금 더 복잡하게 수정을 해줘야겠죠. 그 현상을 묘사할 수 있게. 빔에서는 오일러리 빔 티어리에서 티모세콘 빔 같은 게 추가가 됐는데요. 사실 트러스에서도 이제 다른 방식으로 추가가 되는 비선형성, 우리가 흔히 말하는 소선 거동 같은 거를 묘사를 할 수 있는 트러스 요소도 있고요. 빔 요소들도 있습니다. 그런 것들이 추가가 되면은 아마 건축에서들 이제 제가 아마 마이다스 IT를 첫 시간에 아마 좀 소개시켜 드렸었는데요. 그런 데서 그런 소프트웨어에 대한 임플리멘트를 하고 있는데요. 물론 이제 그런 쪽으로 이제 기술을 개발을 해서 활용을 하는 데도 있지만은 저희 같은 이제 약간 스케일 레벨에서는 어떤 거를 써야 될지 좀 고민이 되고 있습니다. 저도 사실 이제 그래서 그런 것들을 갖다가 이렇게 더 사용을 할 수 있다고 생각을 하고요. 제가 이제 1D를 갖다 좀 더 중점적으로 설명을 해드리는데 이게 처음 유한수를 배우는 거다 보니까 간단한 걸 하긴 하는데 이제 아마 여러분들이 이제 시뮬레이션을 하실 때는 이제 2D 혹은 이제 3D를 조금 더 복잡한 모양을 조금 더 그러니까 조금 더 관심 있는 모양을 조금 할 예정이니까 조금 프랙티컬 문제들로 이제 좀 속도를 내겠습니다. 아마 이번 주에 다음 강의 콤솔 예제는 이제 빔과 이제 똑같은 이제 숙제 문제를 이제 빔으로만 바꾼 거를 갖다 한번 할 거고요. 아마 그 다음 주부터는 이제 거의 이제 아마 스트럭처 프레임 문제를 하나만 좀 더 할 거고요. 그 다음에 이제 아마 2D 이제 넘어가면서부터는 이제는 이제 손으로 풀 수가 없거든요. 매트랩으로 또 코드를 여러분들 짜시기도 좀 힘들고요. 그렇기 때문에 이제 약간 좀 독립적으로 이제 이론과 이제 실제로 프랙티컬 예제를 조금 더 많이 보는 시간을 갖도록 하겠습니다. 그래서 먼저 6주 첫 번째 강의는 여기서 조금 멈추도록 하겠고요. 다음 주 7주부터 약간 좀 빈 부분을 조금 더 이어서 나가도록 하겠습니다. 예, 오늘도 수고하셨습니다.